Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. This is our weekly review of all the stuff we've gone over this week. Let's start off with our first task. I'm just going to go ahead and give you guys a serious task. If you're tracking here, you should be able to do these things without any difficulty. If you are having some difficulty, look and learn how I'm going through this thing. It may help to refresh these things. It may help to even go back and view some of the lecture topics that I'm dealing with again and try some more practice problems. So the first task, what we're going to do, I'm going to ask you to count up in 3-bit binary. 3 bits. Lowest bit is 2 to the 0. The other one, 2 to the 1, 2 to the 2. What are those? It's 1, 2, and 4. Let's start off with all 3 of them zeros. And now the one in the LSB column, I'm just going to alternate that. 0, 1, 0, 1, 0, 1, 0, 1. So every other. Now, in the 2 column, 0, 0, 1, 1, 0, 0, 1, 1. I'm going to put a line here because I don't want you to confuse that. Finally, in the 4 column, every 4. 0, 0, 0, 0, 1, 1, 1, 1. You've exhausted all possible combinations of that. Keeping with this first task, what is the decimal equivalent of those numbers? Obviously, all zeros. It's a 0. When you've got 1, 1, what is it? 1. When you've got 1, 2, what is it? 2. 2 and a 1, 3, 4. You get the picture. 5, 6, 7. Not too hard. Let's expand this down. Go ahead and try to count up in 4-bit binary. So go ahead and pause the recording and see if you can go ahead and do that. And this is what your 4-bit combination should look like. All in all, you should be getting 16. So in our columns here, our LSB is significant. 1, 2, 4, and 8. And again, notice what's happened. The only difference between the 3-bit truth table, the 3-bit count up and the 4-bit count up is notice that the 8-weight digit has 8 zeros with 8 ones. I've exhausted all possible combinations. What are these? The decimal equivalent? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we've exhausted all possible 16 combinations. Our maximum number we can count up to in regular binary is 15. One less than number of positions because 0 counts as a position. Let's use this combination here, this all possible combinations of 4 bits. What if these numbers I want to package up in hexadecimal? What is the hexadecimal equivalent for all these numbers? Well, real easy. These numbers are all the same. The only difference is 10 gets an A, 11 B, C, D, E, F. And that's what that would look like right there. Let's talk about BCD. What do the 4-bit combinations on the left mean in BCD? Well, exact same thing. These are all the same, 0 through 9. What happens when you get to 10 through 15? They're invalid. So BCD is the same thing with an invalid region. And that's what that would look like. Okay, I should have probably done this one when I was dealing with Octal, because Octal only does 3-bit positions. Very similar to hexadecimal and BCD. There's a limited range for this, where it's those 3 bits. 0, 1, 2, 3, 4, 5, 6, 7. So that's just for Octal. We'll go into some conversions between these two systems and talk about Octal a little bit later. But again, there's only 8 positions for Octal. While we're on the topic of codes, count up in gray code in 2 bits, just 2 bits. Again, this is an essential task for later on for Carnot maps. Okay, so gray code, in contrast to binary, only 1 bit changes at a time. To count up in 2 bits gray code, it's 0, 0, 0, 1, 1, 1, 1, 0. So that's gray code, 2-bit. That's all I'm really concerned that you can do in that. Let's go on kind of the heart of the matter here is these conversions. I want you to fill out the remainder of this table without a calculator. So dig what I've got going on here. I got the hexadecimal F1. It's base 16. Convert it to octal. convert it to 8-bit binary, convert it to decimal, then convert it to BCD. This is a lot of work, but if you can get through this whole table, I have no concerns about your ability to convert back and forth between these systems. And I'm going to give you a hint. That column right there is pretty important because you from there can get the octal, can get the decimal. And once you get the decimal, you can get the BCD representation of it. Go ahead and see if you can knock these out by yourself. Go ahead and pause the recording because I'm going to go ahead and do these step by step. F116. Go up to your truth table. What's F in hexadecimal? It's quadruple 1. Maybe this would be a pretty handy thing to have on a cheat sheet and expand upon these cheat sheets. You don't have to write it as messy and big as I do too. You can write these things incredibly small and compact and keep on adding to these things. This is something you can use over and over and over again. I wish I had a stamp for this thing every time I've drawn this thing on a board too. F116. What's F? 1, 2, 3, 4 ones. What's 1? 1, 2, 3 zeros and a 1. Base 2. What is octal? Divided up into groups of 3. There's my first group of 3. There's my second group of 3. There's only 2. What am I going to do? I'm going to pad it with a 0. Going from right to left this time, that's 1. 1, 1, 0 is a 6. 0, 1, 1 is a 3. So it's 3, 6, 1, base 8. Decimal. Try to convert these things all to decimal now. That's why I'm saying that 8-bit binary is an exceptionally handy column to have. What is the decimal equivalent of that? Look at these columns. 128, because it's 8-bit binary. 128, 64, 32, 16, no 8s, no 4s, no 2s, 1, 1. What do you get when you add it all together? 241, base 10. How do I express 241, base 10 in BCD? What I'm sending to 1 7-segment display is the number 2, 0, 0, 1, 0, 4, 1, 0, 0, 1, 0, 0, 1. And I'm just going to call that BCD so you don't confuse them. Keep on trucking along here, see if you can knock out the rest of these things. 137 base 8, again it's groups of 3. What you should be getting here is 1, 2, 3, 4 ones. 1, 0, 1, 0. Strip off that leading 0. Don't need it. Base 2. Which way you want to go first? I don't care which way you want to go first because I'm going to package it up into hexadecimal because it's already in groups of 4. What's that? That's a 5. What's that? F. 5, F, base 16. Do the exact same trick within decimal to convert it to decimal. I've got 164. I've got 116. I've got 18, 14, 12, 11. Add them all together. Should be 95, base 10. How do I express 95 in BCD, i.e. 2 7-segment decoders, 2 7-segment displays, 1, 0, 0, 1, which is 9, and 5, 0, 1, 0, 1, BCD. 8-bit binary, we've got 0, 0, 1, 0, 0, 1, 1, 0. That is 2, 6, base 16. Divided up into groups of 3, what we're going to get for octal is 6, this number, 0, 4, 6, base 8. Do I need that leading 0? No, it's implied. Okay, because what I'm saying is I'm packaging this thing up in groups of 3. Here's my first group of 3. Here's my second group of 3. Where's my third group of 3? It's this one with a leading 0. Well, it's all zeros. Don't worry about it. Okay, so it's just like the 0 suppression I was talking about earlier. You don't need those leading zeros. It's assumed to be a 0. That 8-bit binary number, what does it convert to in decimal? It's got 132, 14, and 12. That's 38. How do I express 38 in binary coded decimal? 3, 8. Don't you wish everything was BCD? Very easy. Decimal, 132. Let's just do the easiest one. 1, 3, 2. That's in BCD. 132. Are there any 128s in 132? Yes. There's no 64s. There's no 32s. There's no 16s. There's no 8s. There is a 4. No 2s, no 1s. 128 plus 4 is 132. Base 2. How do I package this thing up in hexadecimal? 8, 4. Base 16. How do I package the 8-bit binary number up into octal? 2, 0, 4. Base 8. Okay, if you think about this, hex and octal are just shorthand versions of this. I'm just packaging up the 8-bit binary number in groups of 3 or groups of 4. Whereas the BCD is packaging up the decimal number into its individual numbers expressed as a 4-bit binary. Don't know if that makes any sense to anybody, if that helps you guys out. Finally, our last row here, what do we got? We've got a BCD number. It's displaying a 2 and an 8 on a screen. What's it mean? It means decimal 28. Okay, how do I get the 8-bit binary number of 28? No. Yes, there's 116. There's 1 8. There's 1 4. That's 28. Package it up in hex 1 C. Base 16. Package it up in octal 0 3 4. Base 8. Don't need the leading 0. So if you've done everything correctly, you've been given these in green, you should get all those other numbers in the rows. All right, let's move on to kind of something we already kind of went over here, the range of numbers. What is the range of numbers using straight binary that I can express? Let's put it this way. Let me rephrase it. What is the number of positions for 12-bit binary, regular straight binary, that I can express? The number of positions. Well, it's 2 to the 12th. 4,096 different positions. Go ahead and write a 12-bit display of all possible 4,096 combinations. No, just kidding. That would take you all day. That's a lot. What I'm saying is anytime you add a bit, you're doubling it. That's a lot of numbers. What's the maximum positive number I can express, though? Because there are, in this example here, we have 16 different positions, but I can only go up to 15. It's because 0 is one of the positions, so 1 less than that. 2 to the 12th minus 1, 4,095. That's the maximum number, maximum positive number, which is different when we deal with 2's complement. And this is the reason why I left this thing up here. I'm going to go ahead and delete all this stuff here because this is no longer valid. Not all of it is valid. You can still express, package it up in 4-bit packages for hex. Because in, let's say, 4-bit 2's complement, I know we've been doing a lot of 8-bit complement, 8-bit 2's complement. This leftmost bit position is assigned a negative value. Okay, and this goes back to one of our challenge problems we had done earlier. 0, 1, 2, 3, 4, 5, 6, 7. That's the maximum positive number. What do I get when I get here? Negative 8, negative 7, negative 6, negative 5, negative 4, negative 3, negative 2, negative 1. There are still 16 different positions. However, I've just shifted my range, expanded my negative reach at the expense of my positive. Same thing happens when you're using 2's complement. Let's say 12-bit 2's complement. What's the maximum positive number? What's the maximum negative number? Okay, so the formula for that is the maximum positive is 2 to the n minus 1 minus 1. Maximum negative is negative 2 to the n minus 1. What you get there is 2 to the 11th minus 1, 2047 positive. For this other one, it's negative 2048. Count them up if you don't believe me. There's still 4,096 positions, because 0 is kind of a quasi-positive number. 2047 plus 0 is 2048. 2048 plus 2048, 496. While we're talking about 2's complement, let's go ahead and practice some 2's complement. Let's see if you can generate the 8-bit 2's complement of negative 71. And go ahead and pause the recording, because I'm going to go ahead and give you the answer. First step, express it in traditional binary, the positive number, 71. Step 2, invert it. Step 3, add a 1. Get rid of this garbage, you don't need it. 1, 0, 0, 1, 1, 1, 0, 1. This should be your final answer right here. Does it make sense? Negative 128, because again, we are using 8-bit 2's complement where the leftmost bit position is given a negative value. Negative 128 plus 32 plus 16 plus 8 plus 9 gives you negative 71. Okay, try the same thing for negative 110, base 10, because that's confusing. Step 1, go ahead and do the regular binary representation in 8-bit, 8-bit representation. So 110, so positive 110, base 10, 1, 0, 1, 1, 0, triple 1, 0. Step 2, invert it. 1, 0, 0, 1, triple 0, 1. Step 3, add a 1, plus 1. 1 and a 1 is a 1, 0. Bring that 1 down, 1. This is our final answer, 1, 0, 0, 1, 0, 0, 1, 0. Okay, now that you're exceptionally adept at generating the 2's complement, let's actually use it to do something with it. Let's go ahead and see if you can perform the following operation. 36 minus 16. If you've done everything correctly, you better get 20. Okay, so I want you to use 2's complement to perform this. When I say use it, show your work. I've got to be able to see that you can do all this. First off, what we want to do is generate the 2's complement representation of the subtrahend. What's the subtrahend? It's minus 16. So what we got to do is regular 16. What's regular 16? This is easy. Yeah, 116, nothing else. Invert it, add a 1. So you get this ripple effect of 1's that go through. Your representation of 16 should be 4 1's, 4 0's. Now, that is negative 16. What do I do with this number? 2, 3, 4, 1, 2, 3, 4. I'm going to add it with 36. What is the binary representation of 36? Okay, so that's 36 minus 16. Let's make sure that I'm getting it right here. What am I going to do now? I'm going to add them up. 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0. What do I do with this last? Discard it. So it's 3 steps. It's generate the 2's complement of the subtrahend. Step 2, add them up. Step 3, discard that final carry 1. Am I correct? 16 plus 4, oh my gosh, is equal to 20. Okay, so have those means of checking yourself. How do I know that you have this? When I say use 2's complement representation, I have to see that you can generate the 2's complement. I have to see that you can generate the binary representation of 36. I have to see that you can perform the addition correctly and get 20 and discard that final carry out. Okay, so I've got to be able to see there's certain checks that I can see, okay, yeah, this guy's got it or this gal does not have it, or the gal has it and the guy doesn't. Let's do this one. This one's a little tricky. 7 minus 93. Okay, what you going to get as an answer? Negative 86. Just think about that. Is there going to be a carry on this one? We'll see if you're correct. Pause it because I'm going to go ahead and give you the answer here. Generate the 2's complement of the subtrahend. What's the subtrahend? It's negative 93, so I've got to go ahead and generate the 2's complement for negative 93. So positive 93. Invert it. Add a 1. Now what's step 2? So I've generated the 2's complement of the subtrahend. add them up. So 7 plus 1 and a 1 is a 1, 0. 3 ones together is a 1, 1. 1 and 1 is a 1, 0. 1, 0, 1, 0, 1. Was there a carry bit? Was there a possibility? I'm not going to discard anything. The point of the matter is I've got a small positive number added with a large negative number. I'm within that range. There will be no carry. What's my answer? It's negative 86. Am I getting negative 86 right here? Is that correct? Okay, so go ahead and see. Negative 128 plus 64 plus 8 plus 2. What's that? It's negative 86. This is just a little tricky example to show you. You don't discard the final one. You discard the final carry if there's a carry out. In this particular one, there wasn't. Let's see. Next step here. Let me go ahead and draw you something. Here I've got a 7-segment display displaying the number 5. This is a 7447 BCD to 7-segment display driver, which it has its inputs 8, 4, 2, 1 on the left-hand side, being driven by a counter that goes from 0 to 9 and back to 0 to 9. That's what that div 10 on there means. It's 10 positions. It's 9 plus one more position, i.e. 0. That's 10. It's counting. And what I'm asking you is what is on the inputs to the 7447? This is the 7447. What are the inputs of this? What are the outputs of this? This is a common anode 7-segment display. What are the 8, 4, 2, 1 inputs? What is A, B, C, D, E, F, and G, the outputs? Okay, go ahead and pause the recording, see if you can figure this out, because the answer is it's displaying the number 5, what you think the inputs are. It's 5, 0, 1, 0, 1. Now this gets a little tricky. What lights up a segment? First off, where are the segments? That's A, go around it, B, C, D, E, F, go back to the middle, G. Which ones are lit up? Well, A is, F is, G is, C is, and D is. If it's a common anode, i.e. there is a positive all the time on every single LED, what do I got to do to get those LEDs to light up? I just got to give them a 0. That one lights, that one does not. So which ones do I have to light up? I need to light up A, F, G, C, and D. B gets a 1, E gets a 1. I'm turning them off. Okay, let's go ahead and do a very similar question with this one. Okay, now I'm giving you this. The inputs are 1, 0, 0, 1 to the 8, 4, 2, and 1 weighted pins, the 7447. I could just easily call these things D, C, B, A. Some manufacturers might call it that. Just look it up in the pin diagram. I've attached the link to the 7447 data sheets there. You've got it in your packets. So what is that? Well, it's a 9. What you think is going to be on the display? A 9. What's a 9 look like? This. Okay, when a 9 lights up, who's lit up? A, B, C, F, and G. A, B, C, F, and G. D and E get 1. It helps to be able to predict these things. And again, I'm just dividing these things into functional areas. That's my counter. See if it works. See if it's really putting out 1, 0, 0, 1. What is my 7447 sending to my 7-segment display? What is my 7447, what is my 7-segment display receiving from there? Dividing them up into functional areas is absolutely essential to your ability to troubleshoot and repair these things. If one side's working, quit messing with that side. You got to figure out, and most of the times, it's the interface of the system. You know, if you can force a certain amount of force a known condition, you should get a known output. That's how you can test these systems. All right, last but not least, let's try these guys. Go ahead and see if you can figure out the timing diagram responses of signals X and Y based upon the inputs A and B. And I know some of y'all are growing and we're like, wait a second, this is from last week. Check it out, guys. I reserve the right at any time to pull out stuff from the past because this requires synthesis of all this stuff. I know we've spent a whole week on binary numbers here. I'm going to require you guys to go ahead and keep track of it, everything we've learned. These things should still be on that cheat sheet you've got. So again, we're going to be applying all this stuff that we learned this week to the stuff that we learned last week. Let's go ahead and do this. What is output X? What's the gate it is? Well, it's an OR gate. It's got that scoopy back with that pointed end. What's the rectangular symbol for that? Greater than or equal to 1. So our inputs on the left, A, B, X. What does an OR gate behave like? It's high when any input is high. So just walk from left to right. A is high. A and B are high. A is high. Neither of them are high. Walk along. A is high. One of its input is. Get that brief pulse downwards where none of them are. Any input is high. B is now high. A is now high. Back. High when any input is high. Have this on your cheat sheets. You don't necessarily need to have a truth table. You need to know this. What's the second gate? What's the rectangular box symbol for our traditional AND gate? What does an AND gate behave like? Output is high when both, or, because we're going to expand this in a little bit, when all inputs are high. Where are the times when all inputs are high? Right there, and that's it. Okay, because this time right there, A0, B1. 0 and 1 is a 0. So we're taking our truth tables, or, like I said, is use these verbal descriptions of the gates when you're doing these timing analyses. Okay, this is kind of concludes everything I want to review for week 2. You should feel relatively confident with this. We're actually going to go ahead and apply some of this to lab practices and physical devices this week.